All right, welcome back, everyone. Can you hear me? Yes.
Yes, sir.
Yes, sir.
Okay. So I hope you all had a good weekend. Remember how I was having computer problems at the end of class last time? I don't know if y'all remember that, but I had an exciting weekend where I had to completely reinstall my operating system on my computer, which took me an entire day. If you've ever had to do that before, where you have to start over from scratch, pretty much installing all my software, trying to get things to work again. And that was basically all of Saturday. And then I had to grade a bunch of stuff. I'm not trying to play a little, I don't want you playing a violin for me here. I'm just saying I've been very, very busy. I've been sitting in front of this computer for like 4 days straight. So with that said, I think I'm ready for today. And we're going to pick up in 8.1, which is where we left off, and then hopefully get into 8.2. All right. Are there any questions? I was able to get the homework out there, the solution videos. I'm pretty sure they're posted on YouTube. Did y'all see that?
Yes, sir.
Yes. Okay. All right. So I will make sure that I get up the homework solution videos for the next sections later today or tomorrow. Any questions? When did we say we were going to try and do the test? We're off on our schedule here. It's scheduled for April 12th. So I guess we can just leave it there. It's still a couple of weeks away. That's like 3 weeks away. So let's see how things go. We're behind. We're supposed to be starting 8.3 today. We're still in 8.1. So that's not a surprise because we lost time during the winter thing or the snowstorm or whatever. Okay, yeah, so I lost all my notebooks, where I keep all my notes for the semester here. Everything that we've done up to this point, I lost everything. So I think I sent most of you the files through Canvas. So you should have copies of my notes, but I think our last class, I may have lost it. Last class we had. So I'm starting over in 8.1 kind of from scratch, okay? All right, so the main idea here, this is going to be a very important concept as we move forward in this class, is the idea of this inverse trigonometric function. And we spent time talking about what it means to be a function and then what it means to have an inverse. And so we first started with the sine function. And we said in general, the sine function is a function but doesn't have an inverse unless we restrict the domain of the sine function. And so we restrict the domain of the sine function between -pi/2 and pi/2. And if you do that, then all you're going to see if you graph it is this black part of the curve. Now, keep in mind, the real sine function continues like this way, and it goes like this, but we're cutting those pieces off, right? That was the whole idea. We cut it off, so if you look at the black function here, it is a function, passes the vertical line test, and it has an inverse because it passes the horizontal line test. And then we define the inverse function to be this notation, f with a little -1, and then of x equals sine with a little -1 of x. That's called the arcsine function, and another notation for it was arc sine and then x. So there are two notations that we use, but I almost exclusively in this class, I will use this notation. So these are the graphs of the two, right? Here's the original sine function. Here's its inverse in red. And then we said in 6.2, when we talked about 6.2, that anytime you graph a function with its inverse, then they should be reflections of one another over this diagonal line. That diagonal line has the equation y equals x. All right, so this is just visually showing that they are reflections of one another. So here's how we actually, when it gets down to how this works, okay, this is what's happening. We can look at a couple of examples. We should all know this left side right here, we should all know this, okay? This is the values of the sine function at common angles. So if I ask you what's sine of pi/6, everyone here should say, okay, I'm going to go pi/6 on the unit circle is right here. And because we're talking about sine, we are going to be looking at the y coordinate, and everyone should be comfortable with the idea that the answer here should be a half. Okay, so if you plug pi over 6, which is an angle, right? Pi over 6 is an angle. If you plug an angle of pi over 6 into sine, it spits out 1/2. Now, the inverse function undoes that. So if you take the inverse sine of 1/2, then it spits out pi over 6. So it just takes 1/2 back to where it came from. So notice that the input, the thing that goes into the inverse trig function is a number, and the thing that comes out will always be an angle. And I have that written down here, okay? So that's something just to keep in mind. Anytime you put something into an inverse trig function, your answer will be an angle, as opposed to when you go, into the regular trig function, you plug in an angle and get a number. So here's another example, sine of pi over 4. So here we go to pi over 4. Here's pi over 4 on our unit circle. Because we're talking about sine, we're going to be looking at the y coordinate. So the y coordinate here is √2/2. So we get this. Similarly, if we plug √2/2 into the inverse sine, it's going to spit back the pi over 4. Now, here, this last one, sine of negative pi over 3. Be careful here, because where's negative pi over 3? Well, that's down. Let's see, I'm running out of colors here. Negative pi over 3 is actually down here. Okay, it's pi over 3, but backwards. So we're down here and we go grab the y coordinate off there. And the y coordinate is negative √3/2. Oops, I forgot to put the negative. Sorry, negative √3/2. Y'all see that? I forgot the negative there. And then if we plug negative √3/2 into the inverse sine function, it spits back negative pi over 3. Okay, so all the inverse trig function does is takes in a number, spits out an angle. Any questions on that? All right, we can do the exact same thing for cosine. All right, so if we take the cosine function, the regular cosine function looks like this. Starts here, goes down, goes up. That's one period, and then it continues. It goes backwards. So what we had to do is we have to figure out where to cut it so that we get a function that has an inverse. So we decide to cut it right there between 0 and pi. And this is the big difference between the sine and the cosine. When you talk about inverses, it's where we cut them. So here for the cosine, we cut it between 0 and pi. For sine, it was between negative pi over 2 and pi over 2. So keep that in mind, because it's going to be important as we move on. So the inverse cosine function is written with cosine with a -1, and then also you could write that arc cos x. Okay, that's the other notation we can use, but you won't see me use it much. And this is kind of cool because if you graph the cosine function restricted between 0 and pi, and then you graph its inverse function right here, you notice again that they are reflections of one another over the diagonal. By the way, this is called the identity. It's called the identity function. Okay. Y equals x. All right, so the cosine inverse and cosine are reflections of one another over the identity function. So this works exactly the same way as the sine. We say, okay, what's cosine of pi over 3? Okay, so we go to the unit circle, we go to pi over 3. And because we're talking about cosine this time, we're looking at the x coordinate, it's 1/2. So if we do it the other way around and we plug that 1/2 into the inverse cosine, it should spit back pi over 3. And then so on and so forth. Do I need to go through these? Or do you think you understand the idea? Everything's okay? So do you all agree that you kind of have to know this left side? Like you need to know your unit circle. If you don't know your unit circle, it's going to get challenging. Would you agree? Because then it's like, how do you go backwards if you didn't even know how to go forward? Okay, now everything seems like life is good at this point, and then things get a little complicated. All right, so we have to be very careful with domains. All right, so I want you to look at this first example. If I ask everyone here, what's sine of 5 pi over 6? Okay, everyone should be able to do that. So we say, where's 5 pi over 6? So we go on our unit circle, here's 5 pi over 6. Okay, because we're talking about sine, we're going to grab the y coordinate, which is 1/2. Right? So the answer is 1/2. No big deal. Is that okay? Yeah. That's nothing new there. That's all right. But if we do arc sine of 1/2, the answer is pi over 6, not 5 pi over 6. So it didn't take 1/2 back to where it came from. See, 1/2 here came from 5 pi over 6. But here, when we take 1/2 back to where it came from, it's saying pi over 6. Can somebody tell me why? Why is that not 5 pi over 6?
Because of our domain.
Our domain restriction, right? So when you go back to the original definition of sine, of the arc sine, do you all see that we have a restriction here that these are the angles, right? These are your angles that you're allowed to work with. And these are the numbers that will come out. Okay. So remember, if you take an angle and plug it into sine, you get a number that comes out. If you take a number and plug it into the arc sine, it spits out an angle. So right now it's saying if we want to play this game with the inverse sine function, if you want to play the game, then you're only allowed to have angles between negative pi over 2 and pi over 2. So when we're looking at this, 5 pi over 6 was over here in the second quadrant. And so anytime you're talking about the inverse sine, okay, anytime you're talking about inverse sine at all, you are not allowed to be in the second quadrant. In fact, you can only be in the first and fourth quadrants, where your angle would be like this right here is pi over 2. That's the angle pi over 2. And backwards, right, clockwise would be negative pi over 2. You can only be talking about inverse sine over here, which means that this is completely off limits to you if you're going to be talking about inverse trig functions. So when you're doing this, right, if you're going to ask your question, how do you do this then you do not pay any attention to this at all. You say, all right, arc sine of 1/2. So you're thinking to yourself, where on the unit circle is the y coordinate? And I'm saying y coordinate because we're talking about sine. You're saying, where on the unit circle is the y coordinate 1/2? But I can only be in the first or fourth quadrants. And hopefully you can see that that happens right there, right? Oh, shit. Nah, I'll just leave it. There's 1/2 right there, right? So then you go try and find the angle, and the angle is pi over 6. And that's why the answer is pi over 6. Now, I'm not even going to ask if that makes sense. I'm going to give you another one. I'm going to see if you can figure this out. What is arc sine of negative root 2 over 2? So anybody?
5 pi over 3.
So I don't know who said that. Who said that?
Anna.
So what did you say? 5 pi over 3? Where are you getting that from?
Yes.
Explain that to me.
When you look on the unit circle, I'm looking in the fourth quadrant because it's still in our domain, and I'm looking at the y function, or the y
Okay.
coordinate.
The y coordinate right here, this one? And yes?
Yes, sir.
Okay. So does everyone agree? We're looking at, this is going to be the y coordinate on the unit circle, and we're going to look for it, and we see it's right here, right? That's it. So now, Anna Marie, you need to give me the angle that corresponds to that. And what's the angle?
7 pi over 4.
7 pi over 4. Does everyone see that? 7 pi over 4. That is, 7 pi over 4 is not the answer. Why? I agree that that is the angle, but it's not that answer. Because think about what 7 pi over 4 is. See, this is why it's tricky. Okay, think about 7 pi over 4. 7 pi over 4 is the angle that goes all the way around and comes down to here, right? That's 7 pi over 4. You're not allowed to go through the second and third quadrants at all. You must stay in the first or second quadrant, but your angle either must go up like a positive angle, or it must go down as a negative angle. So instead, I think Anna Marie gets it now. You have to go from here to here. And Anna Marie, what's that angle?
Negative pi over 4.
Negative pi over 4. So that is the correct answer. Do y'all see how that can be tricky? Yeah. All right, let me do something here. I'm going to copy this. I'm going to bring it down here. We're going to do another one. Okay, I want to know what arc sine of -1/2 is. Okay, so somebody else want to play today?
Would it be pi over 6?
Okay, so you tell me your thought process. You're looking at -1/2, and then what are you thinking?
Well, because if you look at the y value, it's -1/2, so you would go down to 11 pi over 6, but since it's going all the way around to the fourth quadrant, you can't really do that. So
Yeah, we can't go over here, so we can't have an angle that comes all the way around, right? We can't do that, so it has to go. Keep going. You're saying this perfectly.
you would have to go the other way.
This way. Okay, what's that angle?
Pi over 6.
Negative.
Negative pi.
Negative. See, because positive pi over 6 is up here, right?
Mhm.
That's pi over 6. But you wanted to go down, right? So that's negative pi over 6.
Oh, okay.
Got it?
Got it. Thank
You were almost there. I mean, that was almost right, but good. This is the whole idea, is that you understand and learn, right? That makes sense, Cameron?
That makes sense. Thank
Good.
you.
Good. All right. Now, the same thing happens when we talk about the inverse cosine. Okay. The same thing happens when we talk about the inverse cosine. We have to be careful. So I think what I'm gonna do is I'm going to copy this down to a new page. Let me go back and grab this. Let me go grab a unit circle real quick. All right. Make this a little bigger for you. Okay, so look, if we say what's cosine of negative pi over 3? Okay, cosine, not our cosine, just cosine. This is back from previous classes. Cosine of negative pi over 3 means we're going to look for the x coordinate at negative pi over 3. So first, where is negative pi over 3? Well, negative pi over 3 means we move clockwise to here, right? That is negative pi over 3. And so here's our angle. And we're going to go grab the x coordinate. And so that's why that answer is 1/2, right? But if you say what's inverse cosine of 1/2, you do not get negative pi over 3. And the reason why is because there is a domain restriction for cosine when we talk about inverses. And let's go look at that again. The domain restriction is that your angles can only be between 0 and pi. So when I go and look at this, what quadrants can you not look in? If you can only be between 0 and pi, what quadrants are off limits? The what?
3 and 4.
3 and 4. You're not allowed to look here. Okay. So when we're doing this problem right here, and we're saying what's inverse cosine of 1/2, you have to look at, you're looking for the x coordinate, and you're looking for where is the x coordinate 1/2. So you look around, you say, ah, there it is. There's where the x coordinate is 1/2, right? And then you say, what's the angle that corresponds to that? It's pi over 3. You see? And that's why the answer is pi over 3. Okay. I'll do one more of these with the inverse cosine. Inverse cosine of -√3/2. So you're looking for where, well, someone tell me. I need another volunteer. Caroline, did you?
It's 5 pi over 6, right?
5 pi over 6, good. So you're looking for the x coordinate. Where is it -√3/2? Well, there it is. And then you look for the angle 5 pi over 6, and then that's your answer. Now, I think, I'll be honest, with inverse cosine, everything is better than it was with inverse sine, because with inverse cosine, it's either the first or second quadrants, and those angles are always positive, where with the previous example, because we could be in the fourth quadrant, those angles had to be negative angles because we weren't allowed to go all the way around. So I would say inverse sine is more complicated than inverse cosine. All right, that's just my opinion. Do I need to go through any more of these for inverse cosine? We're going to get more practice. Don't worry. I mean, it is going to come. All right, so we have to be careful with domain restrictions. All right. Now we have we have tangent function and we have its inverse. Okay. Now this one is weird. Okay, tangent is a weird function. It's got a weird inverse. So remember that when we graph the tangent, it's been a while since we graphed tangent, but when we graph tangent, it looked like this. At pi over 2, it had a vertical asymptote, negative pi over 2 had a vertical asymptote, and then it looked like this. Oh, oops.
I have a quick question.
Yes.
For the inverse cosine, if
Mhm.
the x coordinate was in the third or fourth quadrant, would that mean, like, would we just act as if it was positive, or would we say that it wasn't possible?
I think I understand what you're asking me. You're saying, okay, if the x coordinate was in the third or fourth quadrant. So give me an example. Just pick one. Pick an example of an x coordinate in the third or fourth quadrant.
Negative root 2 over 2.
Negative root 2 over 2. So you're asking me what would happen if we had cosine inverse of negative root 2 over 2, right? That's what you're asking?
Yes.
Okay, so where is that one? That one's here, right here, right? That's that one? Okay, my answer to you would be, Maddie, you're not allowed to look down there.
Okay.
So that forces you to be looking at that one. You see, these two have the same x coordinates. Do you see that?
Oh, yeah. Okay.
And so that would have worked for any x coordinate you pick down. Like, let's say you pick the 1/2 down here in the fourth quadrant. Well, I tell you what, there's one up here. You see, so you would go off of this angle instead.
Gotcha.
That makes sense?
Thank you.
Okay, good question. All right, so for the tangent, you know, we were saying this is what it looks like, and then it just kept repeating itself, right? Kept repeating itself. So what we do is, again, we try and restrict the domain so that we have a one-to-one function, something that passes the vertical and horizontal line test. And so what we do is we look at the one just in the center here. And so that's what this note is saying. If we look at the tangent function and we just go between negative pi over 2 and pi over 2, and I will also point out, notice I don't have equals underneath those inequalities. The reason I don't have an equal under here is because you cannot plug in pi over 2 or negative pi over 2 into tangent. If you try, you'll get division by 0, and that represents those vertical asymptotes that we have. Right? Do y'all see that this black function here, that's our tangent function? Do y'all see it has 2 vertical asymptotes? Okay, so when we restrict our domain on tangent between those 2 yellow verticals, then we have a nice one-to-one function. Its inverse is this red one, okay? That's what its inverse is. And notice again, it's a reflection of itself. Okay, it's a reflection of itself over the identity function. Okay, this is an important part right here that I want to see if somebody can answer this. I haven't really talked about it yet, but I'm going to see if someone can answer this, because the tangent function is very different than the sine and cosine, right? Remember, sine and cosine they're both bounded. They only go between -1 and -1 and 1, right? Both sine and cosine. But here, the tangent function, can somebody tell me well, let's start with this. If I ask you for the tangent function, just looking at it right here, what's the domain that we're talking about? The domain of this black curve? Where are we restricting it?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. Now, let me ask you about the range. That means the things that come out. So when you look at that black curve, tell me about the outputs. What things can come out?
Anything.
What's that?
Negative infinity to infinity.
Yeah, anything, right? Any number can come out. You could have any negative number, because this graph goes down and keeps going forever. And then it keeps coming up and going forever. So the range of the tangent function is every number between negative infinity and infinity. That's the outputs. And remember that when you do an inverse function, the domains and ranges switch places. In other words, if I have tangent of x, here's the domain. And we said that's negative pi over 2 to pi over 2, everything in between there, right? Everything in between here. The output is basically any number, negative infinity to infinity. This is the outputs. So the inverse tangent goes the other direction. And that means that we can plug any number into the inverse tangent and it will spit out an answer, right? Anything, any number we ever pick can be plugged into the inverse tangent function. It will spit out an answer. It's just that the answer will be between negative pi over 2 and pi over 2. So you can see that if you look at the graph, notice the red graph, the red function here. That's our inverse tangent. Do y'all see that its domain is everything? Like it goes to the left and right forever, this graph. But it's also bounded, which means the outputs, the blue lines, dotted lines here, restrict the output of the inverse tangent function. It's between actually negative pi over 2 and pi over 2. So if you get that, you get that. If you don't worry about it too much. It's not going to mean you can't move on in the class. It's just, it's something that is different when it comes to the tangent function that wasn't like that with sine and cosine. Okay. All right, now we have this very important thing called the cancellation property. It's an awesome property, but it's extremely dangerous. All right, so all this says, and this goes back to the idea of inverse functions. When we were studying 6.2, we said, if you take a function and put it together with its inverse, they undo each other and then it just spits out x. And we actually had to show that it was true both ways. You'd have to go back and look at 6.2 to see when we talked about this. This is what it meant for two functions to be inverses. You plug in x, send it through the inverse, and then send it through the function. It'll come out unchanged. You change the order, and it does the same thing. So this was when I was talking about, like, you have a car wash, right? You send your clean car through the car, I mean, the dirty car through the car wash, it gets clean, but then if you send it through the inverse car wash, it would come back dirty. That's basically what happens here. So that's what these properties are saying. If you take the sine function and take sine of its inverse of x, then it's just going to spit out x. And it works the other way around. And it works for all three of these trig functions. But we have domain restrictions that we always have to be paying attention to, right? We always have to pay attention to those. So I'll give you an example. Let's start with an easy one. If I do sine inverse of sine of pi over 6, let's see. According to this property, what does it seem like the answer should be? According to this cancellation
Pi over
property.
6.
The answer should be pi over 6. Well, I'll tell you what, that will be true as long as the x you're talking about is between negative pi over 2 and pi over 2. So is this question, is pi over 6 between pi over 2 and negative pi over 2? Yes or no?
Yeah.
Yes, because, you know, pi over 6 is right here, right? And negative pi over 2 to pi over 2, that's in the first and fourth quadrants. We're okay. All right. So that is the answer. But what about this? Sine inverse of sine of, let's go 2 pi over 3. A lot of people will say incorrectly that this answer is 2 pi over 3. But that is incorrect. Right? So the cancellation property makes you think you can always just, oh, you just put them together and it just cancels out and you just get this as your answer. But it is not the case. Let me go and grab my unit circle here. So let's see what the answer is here. So this would be true. This would be 2 pi over 3 if 2 pi over 3 was in the first or second quadrants. 2 pi over 3 is right here. That's this angle right here. Well, that's not in the first or fourth quadrants. That's in the second one. We're not allowed to use the cancellation property. Can we still get an answer though?
It'd be pi over 3, correct?
Yeah, let's see how we get to that. So first thing we would do is just say, okay, what's sine inverse now? Let's just figure out what is sine of 2 pi over 3. So just what is this? Sine of 2 pi over 3. Well, you're looking for the y coordinate 2 pi over 3, right? What's the y coordinate?
Root 3 over 2.
Root 3 over 2. So this is just sine inverse of root 3 over 2. Right, that's all that is right there. And now you say, what's arc sine of root 3 over 2? But you're only allowed to look in the first and fourth quadrants because we're talking about the inverse sine. And so now you're looking for where's the y coordinate root 3 over 2, and you can see it right there. Do y'all see that? There's your y coordinate is root 3 over 2. So what is that? Let's see. What angle is this?
Pi
Pi
over
over 3.
3.
So your answer is pi over 3. Okay, so I hope that that illustrates how things can be dangerous. What we just concluded was this. Arc sine of 2 pi over 3 is actually pi over 3. So the cancellation property did not work in that case. All right. We'll do some more of those. All right. I always tell my students, my pre-cal students, and this is probably not the first time I've told you this, but and you'll hear me say this again. You know, I teach calculus. I mean, most of the time I teach calculus, and my pre-cal students always walk into calculus and they all have strengths and weaknesses. And I always tell them, if there's 2 things that you can take from pre-cal that you need in calculus is you need to know your unit circle. So you need that. When I say that, means you need to know that thing like the back of your hand. All right. I don't know. You always say that, but I don't know the back of my hand very well. But anyway, you know it's a figure of speech, right? Okay. So the unit circle you've got to know. So sine of certain angles, cosine. But the other thing you need to know is how to solve trigonometric equations. And this is our first glimpse into it. Okay. We're gonna do a lot of this later, and it's gonna be a lot more complicated. But this is our first kind of introduction into solving a trig equation. Because that's the ultimate goal of all this. We want to solve equations. All right. We will be doing this later. All right. So let's take a look at this first equation. We are being asked to solve this equation for x. So I want to know what x I plug in there to make that true. So this is just like me giving you an equation like this: 2x plus 4 equals 6, and I ask you to solve, right? So you'd solve that. I mean, we have ways of solving this, don't we? We would just like subtract 4 on both sides, right? And then we divide both sides by 2, and we get the solution x is 1, right? So that's a linear equation, right? That's a linear equation back from college algebra. Then in college algebra, we also had like quadratic equations and different types of equations, right? Square root equations, blah, blah, blah. Now we're trying to solve a trig equation. So we're going to go through some sort of procedure here. We're going to do almost like we just did with the linear equation. I'm going to add 1 to both sides. So I get 2 sine of x equals 1. And then I'm going to divide both sides by 2 because there's a 2 in front of that sign. So I'm going to get sine of x equals a half. Yes? Now the fun part. What is this saying? Can somebody tell me what this is asking us for?
It's
y.
asking.
Y coordinate.
The y coordinate is what? Is it asking us for the y coordinate, or is it asking us for an angle?
It's asking us for an angle.
It's asking us for an angle. It's saying, what angle do you plug into sine to get 1/2?
Pi over
What
6.
angle do you plug into sine to get 1/2? Right, that's what it's asking. Can somebody tell me what angle I plug into sine function to get a half?
Pi over
6.
Pi over 6. Do y'all agree with that? Look, the y coordinate here is 1/2. We got pi over 6. Do y'all agree that that's an answer? Yes, yes.
Yes. Wait,
Okay, is that the only answer?
no, wait, can we have more than one answer when it
Oh,
comes?
yeah. Oh, yeah, we can have more than one. We're actually gonna have an infinite number of them.
5 pi
Right.
over 6.
5
So-
pi over 6. So here,
Yeah.
look, there's another place where the y coordinate was 1/2, and that was happening at 5 pi over 6.
I have a quick question.
Yes,
Does the domain not matter here then?
great question. I was hoping you would ask. Anna Marie's asking, do we have a domain restriction right now? Are we only allowed to look in the first and fourth quadrants because we're talking about, right? Well, do you see inverse sine here anywhere? Do you see arc sine?
No, sir.
Right? We're just dealing with the sine function. So there is no domain restriction right now. So we are allowed to look anywhere on the circle, okay? Anywhere we want. And so we have found so far two solutions to this. Pi over 6 is one of them, and the other one was 5 pi over 6. Are there any other angles on the unit circle right now that you can see where the y coordinate is positive 1/2? No, right? That's it. Okay, now let's look at these one at a time. Now I put this unit circle up here for you. Okay, I put that up here, but I'm going to show you right now the way that I do it when I'm working a problem like this. All right, what I do is once I get to this point right here, I draw myself a quick circle like this, and then I already have memorized where the y coordinate is 1/2, and I know it's here and here. Those two things I've got memorized. And I already know that this is pi over 6 and that's 5 pi over 6. So I draw these two little dots on a unit circle. All right. If I don't know the unit circle, if I don't have that memorized, then this doesn't make any sense to do this. But that's what I do. Okay. And then I start with the first angle and I ask myself, how can I represent that angle as an answer? But I need to include all infinitely many coterminal angles to that angle. So remember, this is pi over 6, right? But what if I started here at pi over 6, but then decided to just go around again? Then I could do pi over 6 and I could add a full revolution and I would be back there, right? That would be the same angle. That'd be another answer. Or I could have added like 2 full revolutions. So I could have done, oh, sorry, I don't know why I put pi over 2 there. Or I could have done like pi over 6 plus 2 full revolutions, which would have been 4 pi. Or I could have done 3 full revolutions, or 4, or 5, or 6, or doesn't matter how many, right?
Is it going to be pi over 6 plus 2 pi k?
2 pi k, exactly. Plus, so our answer, one of our answers, okay, is pi over 6 plus as many full rotations as you want. So 2 pi is a full rotation, and then times k, where k is an integer. Remember, yes or no, we've talked about k before and how we can use k to include rotations.
So k would be an integer, not a natural number.
It can't be a fraction. It can't be like 1/2. K has to be either 0, 1, 2, 3, 4, 5, 6, 7, 8, or you could even have -1, -2, -3, -4. You're either adding clockwise rotations or counterclockwise, but they're full rotations. Does that make sense, Maddie?
Yes. Then how would you account for the other angle?
The what?
How would you account for 5 pi over 6?
Okay, yeah, so we're only halfway there. So right now we've only taken care of the pi over 6 and all of the coterminal angles to pi over 6. Now we have to look at this guy over here. That angle is what, 5 pi over 6? But I can also get full rotations back to 5 pi over 6, can't I? So it'd be the same story. X equals 5 pi over 6 plus any 2 pi k full revolutions, right? And so that's it. That covers all the answers. I have an infinite number of solutions to that equation. What do y'all think?
I have a quick question about
Uh-huh.
k. If you were going clockwise, does that make k negative?
That's right. No, K would be, if K is positive, you're doing counterclockwise,
Mhm.
which is like this, right? That's if K is positive. If K is negative, then you're going the other direction. So
Okay.
this is K negative. Oops. Let's do it this way. K negative, K positive. Yeah.
Thank you.
All right. Let's see if you understand that. I want to just try another one real quick. What if I asked you for the solutions here? Cosine of x equals, this is just an equation I'm just throwing out there for you. Cosine of x equals negative root 3 over 2. All right, so cosine of x is negative root 3 over 2. So now I'm going to go to what I know about the unit circle. Now you have a unit circle, I'm sure, somewhere. I'm going to just, again, show you how I'm thinking about this. Cosine is the x coordinate, right? Cosine is the x coordinate. I want to know, where is it negative root 3 over 2? And from my knowledge of that, and we'll double check in a second, that should be here. And that should also be here. Those should be the two angles. This first one is 5 pi over 6. We just did that one, right? And this one was 7 pi over 6. Now, where'd it go? Now we'll check to see if I got it right. See, we want the x coordinate to be negative root 3 over 2, happens here and that here. So do you see how me knowing the unit circle, like knowing it, makes this a lot easier, because I can just like draw my two dots and then I'm ready to go. Now, what about rotations? Let's get all these answers. So it would be x must be equal to this angle, 5 pi over 6, plus 2 pi k again. That gives me all full revolutions, getting me back to there. And then I also have another set of solutions, 7 pi over 6 plus 2 pi k. Any questions? I have another one for you then.
I have one question.
Yep.
So at the end, we'll always have the 2 pi k.
No. Let me give you another example. All right. Let me give you another example. I cannot say yes to that answer. I'm sorry, to that question, because it's not always true. So here comes an example. What if I say, solve this equation? Cosine of x equals 0. Okay, so James, here we're going to go to our unit circle and we're looking for where what coordinate is what. We're talking about the cosine, so that's which coordinate?
The cosine, or so since we're finding a cosine, that's going to be the x.
The x coordinate, and we want to know where's the x coordinate 0. Okay, so looking on your unit circle, where's your x coordinate 0? At what angle or angles?
Can anyone answer?
Yeah, no, I just wrote them. I just drew them there. But yeah, anyone can answer. Caroline, what were you going to say?
It's 0 and pi.
The x coordinate? I think you're looking at the y coordinate,
Oh, yeah, the x. Okay.
right?
sorry.
Do y'all see that these two red dots, that's where my x coordinate is 0, right? If you go write those points 0 and 1, and then this one is 0 and -1. Those are those
So
points.
It'd be pi over 2 and negative pi over 2.
Yeah, so you could look at this. There's different ways you could look at this. You could say that this angle is pi over 2. And you could say this angle was negative pi over 2. Or if you wanted to, you say that that angle is 3 pi over 2. Y'all agree with that? So look, I'm gonna write something down. I don't want you to write this down. I just want you to just let me write it down and we'll talk about it. Okay, this first answer, x equals pi over 2 plus 2 pi k, gives me that point, or gives me this angle, and then I go fully back to it, right? Fully back to it, fully back to it, full rotations. Then this one gives me the angle down on the bottom, and then full rotations would get me back to it, right? And so this would be correct, right? There's nothing wrong with what I've done here. Do y'all agree? That makes sense? But I have a different way I want you to look at it. Because even though this is correct, I want you to look at, if I were to just look at this angle here, okay? That's the angle pi over 2. Because the other angle is directly across from it, right? Like this is directly across, then couldn't I go to pi over 2, start at pi over 2, and then add to it, not a full rotation, but add a half rotation, and that would take me to the other answer, right? And then add another half rotation, and that would take me back to this one. And then another half rotation would take me back here, another half rotation back here, another half back here. So why not just put pi over 2? What's a half rotation?
Pi.
Pi, not 2 pi is a full rotation, right? So half of a rotation would be pi k. Full rotation, but this would be a half rotation. Does it make sense? This is a more efficient answer because it covers every answer that's in here in a much cleaner, condensed form. James, do you see that now, that it doesn't have to be 2 pi k all the time?
Yes, sir. And I see how like you brought both of them like together.
Mm-hmm. This kind of kills 2 birds with 1 stone. All right.
Would there be a certain instance when you need to choose like one over the other?
When you what?
When you need to choose like one over the other, like either 2 pi k or pi k?
No, it just depends on the problem. It just depends on the problem. I mean, I always like to be as efficient as possible. I have one more example for us to do, and I think you'll see what I'm saying. We're going to do this example right here. So we're trying to solve the equation 4 cosine squared x minus 3 equals 0. Okay, so first thing I need to do is clarify something. When we see this written down, this is the notation we use in math whenever we want to square the cosine function. What you need to understand, and do not forget, is that this just means you take the cosine function and square it. You're not squaring the x, you're squaring the cosine function. The reason we don't write it like this is because people will think you're squaring the x here. They'll think, oh, this is cosine of x squared. No, we want to square the whole thing. So to square the whole thing, we could write this, or this is the notation we use. It's just another way of writing this. I hate this notation because it confuses students, all right? But this means
I have a
this.
question.
Yes,
If it's written as cosine x squared, then does that mean that
Like
does that mean that we square the x before we
That
take
is
the
right.
cosine of it? Okay.
That's right. So this right here would be the same as cosine of x squared. That's what this would mean. And because it can be confusing, we use this notation to mean this, so that you don't accidentally, like this 2 looks out of place, doesn't it? Like it looks like it's in the, like just misplaced. Well, we do it intentionally so that you know we're not squaring the x, we're actually squaring the whole cosine. All right, so back to this. Let's solve for x. So first thing I'm gonna do is add 3. And I'm actually gonna write this like this now, just because this is our first example. And now what I'm gonna do is I'm gonna divide both sides by 4. Go with me? Now, if I'm trying to get x by itself, I'm gonna need to get the cosine of x by itself. So how do I get rid of a squared?
Square root.
Square root. both sides of the equation. And we've talked about this already. What happens when you are the one who comes in with the square root on both sides of an equation? You have to do
Plus or minus.
plus or minus. And I think, was it Maddie that you asked last time? Do you have to do plus or minus on both sides? Remember that? Was it you, Maddie? Yeah, so we only have to do it on one side because it basically gives you the same thing if you do it on both sides. And so the left side here becomes cosine of x, and the right side becomes plus or minus. Now, square root of 3 over 4, because you have a fraction under a root, you can do the square root of the top and then the square root of the bottom. What's square root of the bottom?
2.
2. Okay, so look what we have now. Cosine of x needs to be plus or minus root 3 over 2. Cosine of x is the x coordinate. So I'm going to go to my unit circle. I want to know where my x coordinate is either positive or negative root 3 over 2. Do y'all see where those happen? This is where it'll be up to you to figure this out. It's happening here, 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 and here. Yeah? Do I have to bring up the unit circle? It's right here. I'll highlight them in blue. I'm looking for my x coordinate being positive root 3 over 2 or negative root 3 over 2. So those are the places it happens. So this is at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So if you wanted to, you could write each of those down and add 2 pi k to each one. If you wanted to, you could write 4 different answers down and just adding 2 pi k to each of those answers. What would be a little bit more efficient? Does anyone see how we could kind of kill 2 birds with 1 stone here?
Yeah.
How?
So I would probably choose pi over 6 and 5 pi over 6. And I would say x equals pi over 6 plus pi k. So we could get 7 pi over 6.
Okay, so good. Pause for a second here. Let me just make sure everyone understands. Joshua was saying, look, pi over 6 and 7 pi over 6 are directly across from one another. And so I can efficiently jump from one to the other by just adding half rotations. Perfect. That should take care of half the answers. Now, what about the other half, Joshua?
And then I just chose 5 pi over 6 and I did the same thing. I added pi k.
Pi k. Now Joshua was saying, now if I start here, right, at 5 pi over 6, then 11 pi over 6 is directly across from it. So we should be able to just jump again by half rotations. And that should take care of it. So you'd have those 2 sets of answers. Would this have been correct? Instead of that answer, could I have done this? Instead of pi over 6 plus pi k, could I have done 7 pi over 6 plus pi k?
Yes.
Yeah, because this is saying start here, okay? Start at this angle, and then again, just jump by half rotations. And if you do that, you're just going to be back and forth between these 2 dots. So it doesn't really matter where you start as long as it's one of those angles and you're in business. Okay. I have a tricky one for you. Last one. How about I give you a moment to see if you can't figure this out on your own? I want you to solve for x. I'll give you about, I don't know, 3 minutes. All right. Samuel, are you there?
Yes.
Are you getting anywhere here?
I didn't get to finish it.
Okay. Michael, you there?
Yeah, I'm here.
Okay. Allison, you there?
Yeah, I'm here.
Leslie?
Yes, sir, I'm working on it.
Okay. Jordan?
I'm here.
Okay. Jackson?
Hello. Yes, I'm here.
All right. Brianna?
Here.
Okay. So Young, are you there?
Yeah.
Karen?
Yes.
Quinn?
Yes, I'm here.
Quinn, are you there? And Halik?
I'm here.
Okay. I'm just letting y'all finish up. I had to post midterm grades yesterday, so you might get an alert in an email saying that like you're at risk of not passing the class. Anyone who has an average right now below 70 got an automatic thing. So, you know, it's an invitation if you're not passing just to come into my office hours if you need help. You know, I'm here for you if you need me. Just let me know. I'm just letting you know it's like an automated thing. It's not like I went out and actually chose to do that. I have to do it. The school requires that I send those out. So, okay, y'all ready to go through this? Does anyone feel like they got it?
Yeah, I think I got it.
Possibly.
Okay, possibly. Okay, so there are different ways to go about this, but I think the most natural way would be to first move the 1 to the other side, and then take your square root on both sides. When you take your square root, you'll get plus or minus square root of 1, which is really just plus or minus 1. Okay, now, if we have that, then what is that really asking us? Because if it's sine or cosine, we're looking at the x or y coordinate, right? But here, if it's tangent, what are we looking at?
Y over the x.
The y divided by the x, right? So where is the y divided by the x equal to 1 or -1? And I think I will bring up the unit circle here. This you should, if you don't know this already, you should know this, all right? That whenever you're looking at the unit circle, there are certain places here where the y and x coordinates are exactly the same, right? Here, root 2 over 2, root 2 over 2. If you were to take the y and divide it by x, you get 1. Same with down here, right? Those are the same. Negative root 2 over negative root 2 over 2 and negative root 2 over 2. If you divide those, y divided by x, you get 1 again, right? And then you have this right here and this right here. They're the same, but they're off by a sign. So if you divide the y by x there, you get -1, don't you? So we really are looking at a circle and we're looking at these angles here, 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 and here. Now, what is the most efficient way to represent those answers? Does anyone have? You can get it all in one answer. Does anyone have it with one answer?
I have it.
What do you have?
Pi over 4 plus pi over 2k.
Perfect. So can you explain to us how you got that, what you're thinking when you did that?
Well, I break it down completely. So I start with the 4, just so I can have it all written down. I start with each one individually.
Mhm.
And then I went over and I was like, well, we could do it in half rotation. So then it would just be pi over k. But then when you look at the unit circle and how it's, I count by 2. So it's
Yeah.
the middle line and then to the next one. So that'd be 2. So if you put it pi over 2, then
Yeah.
you get to the next.
Good. Exactly. So what Brianna is saying is, first, she noticed that this is pi over 4, right? That's angle pi over 4. But because of the natural placement of these 4 points around the circle, these are all right angles, aren't they? This is making like a perfect T, isn't it? And that means this is 90 degrees. That's pi over 2, right? So what we could do is start at pi over 4 and then jump by pi over 2, then jump by pi over 2, then jump by pi over 2, and then jump by pi over 2. And then we just keep on jumping. And so we can jump across and just hit all four and just keep doing it over and over and over and over. And so start at pi over 4. That's where you start. That's the start. And then this is the jump that you're going to make. And then the k is just going to be how many jumps you make. Does that make sense, everyone?
How come we didn't do that for the previous one?
Great question. Why didn't we do that for the previous one?
Because the intervals weren't even between all four
Yeah.
coordinates.
Where was the previous one? I got to find the previous one.
Or maybe it wasn't the previous one, but one of the previous ones.
Yeah, there was this one right here. I think this is the one you're kind of referring to, Maddie,
Mhm.
where we had 4 different answers. Notice that
Oh, I see.
notice that they're not directly across from one another, right? So like
Gotcha.
the x here is like squashed down. And so if you tried to jump from this one to that one, that wouldn't be like pi, it wouldn't be pi over 2. And then the jump from here to here wouldn't be the same angle. So the only way you can do the jumps is if it's the same increment between the angles each time.
Gotcha.
Like on this one here, they were directly across from one another, so we could just go pi each time, pi, 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 pi. Here, pi over 2 between each one, so we go pi over 2. That makes sense, everyone?
Yes, thank you.
Okay. All right. I think we're ready to move on. All right. So we have talked about the inverse trig functions, arc sine, arc cosine, arc tangent. And we've done some work with them, and we'll continue to do work with them. And you'll hopefully become very familiar and comfortable with those inverse trig functions as time goes on. But there are also 3 other inverse trig functions. We have an inverse for the secant, an inverse for cosecant, an inverse for cotangent. Now, these are not used as frequently as the first 3 are. In fact, they're used so infrequently that I'm just going to present them to you here. Here's the definition of them. There are some domain restrictions, but that's all we're going to say about it. Okay, if we need these, we'll come back to this. We're not going to go through a full like breakdown the way we did here with examples for those 3 inverse trig functions. All right, let's just know they exist, know that there's domain restrictions, and if we need to work with them, we will later. I will also point out that on your formula sheet, okay, if you go to your formulas, I gave you the formulas for the calculus that we use in calculus. If you go to the reference page here, I think there's 6 pages here. If you go to reference page 3, on the bottom here, it shows you the 3 most important inverse trig functions, and it actually includes the domain restrictions. So as you move on to calculus, if you forget the domain restrictions, this will remind you of what they are. For sine, we go between negative pi over 2 and pi over 2. For cosine's inverse, we go between 0 and pi. And for tangent, we go between negative pi over 2 and pi over 2, not including the endpoints. All right, so just know that that's there.
We're allowed to use that formula sheet on the tests, right?
You are, yes.
All right.
Mm-hmm. And in calculus, so professors are different, okay? Like I've always allowed my students to use formulas on their tests. Some professors don't. And that's just a personal preference thing. My opinion is that, you know, what we're really trying to do is get you ready for the real world, like a real job. And in the real world, when you're trying to solve a problem, you're never going to be like trapped in a room with no references, you know, like unless you're out on a desert island, you know. Otherwise, if you're trying to solve a problem, you're going to be working with a team. You're going to be able to look things up. You know, I'm not talking about solving math problems. I'm just solving like whatever problems you're trying to do, right? If you're computer programming, you're trying to write a program. If you're engineering, you're trying to build a bridge. You're going to be working collaboratively with other people, and reference material is something you will have access to. So that's why I always believe formulas are fine to have on tests. All right, we're moving on. Same section. We're going to do some problems now that are just going to seem like they're coming out of nowhere, right? We're going to do a couple of these. And I want you to put a star next to this, because let's put 2 stars. 2 stars for Cal 2. This stuff comes up in Cal 2 quite a bit, all right? Well, not these particular problems, but the method we're going to use to solve these problems comes up in Cal 2. All right, so here's what we're going to do. Let's start out with this first one. Cosine of arc sine or inverse sine of root 2 over 2. All right, so notice that we're taking cosine of the inverse sine of the square root of 2 over 2. So just real quick, can somebody tell me what this spits out? Does that spit out an angle or does that spit out a number?
An angle.
An angle, okay? That spits out an angle. Do you all agree? Whatever it is, it is. And then we're supposed to take cosine of that angle. So I'm going to call this theta. How about that? So do you all agree that we want cosine of theta? Right? That's what we want. We want cosine of theta. And we have that theta is equal to sine inverse of root 2 over 2. Right? That's what we called it. This right here, we called it theta. We want to know what cosine of theta is, and theta is equal to this. Now, do you agree with this? This really means we're trying to figure out what angle you plug in to sine to get root 2 over 2. Do y'all agree with that? That's what this is really saying. This right here means go get me the angle that when I look at the y coordinate on the unit circle, I get root 2 over 2. So that's this same equation, isn't it? Now, can somebody tell me what that is?
Pi over 4.
Pi over 4. Okay, I agree. That's pi over 4. Because this is saying where on the unit circle is your y coordinate pi over 4, right? That's saying where is, sorry, not pi over 4. This is saying where on the unit circle is your y coordinate root 2 over 2, which is here. And you're not allowed to look over here. Why am I not allowed to look over here?
The domain.
Domain, because inverse sine, I can't look in the second or third quadrants. And so this is going to be pi over 4. So my answer here is that theta must be pi over 4. Now let's go back to what we wanted. We wanted cosine of theta. What's cosine of pi over 4?
Square root of 2 over 2.
This is the x coordinate, right? We go to pi over 4, we look at the x coordinate. That happens to be root 2 over 2. And so the answer here is root 2 over 2, the x coordinate. All right, so we said cosine of some angle. We want to know what that is. The angle is coming from arc sine of root 2 over 2. And then from that, you said, all right, well, we know that that angle corresponds to pi over 4 on the unit circle. And then we just plug pi over 4 into cosine, we get root 2 over 2. Questions there? I'm going to do another one, but I just want to see if there's any questions on that.
To write the final answer, you'd take the original problem and then put square root of 2 over 2 as the answer, correct?
This is like that?
Yes.
That is that, yes.
Okay, thank you.
Okay, let's do another one. Sine of cosine inverse of a half. Sine of cosine inverse of a half. So again, this should spit out an angle. I'm going to call it theta. We want sine of theta, right? We want sine of whatever that angle is. But theta is cosine inverse of a half, which means we're looking on the unit circle. We're looking for which coordinate, x or y?
X.
X, where the x coordinate is a half, and we're not allowed to look down here. Because again, the domain restriction for cosine inverse. So that should be happening right, I think it's here, right?
Pi over 3.
1/2 root 3 over 2 is the coordinate, and the x coordinate there is a half. So that angle, you said was what, pi over 3?
Yes, sir.
Yep. So this is going to be theta is pi over 3. So now let's go back to what we wanted, right? We wanted this. So sine of pi over 3. So that should just be the y coordinate there, shouldn't it? And that's just root 3 over 2. So far, is everything going naturally here? Everything seemed to be flowing okay?
So far, yeah.
So far, okay, it's about to get weird. So let's do, trying to see which one I want here. Where's a harder one? These are all. These are all using common angles. Let me try, let me make one up. Again, because of where we're headed. Sine of cosine inverse of 1/3. Okay, here we go. This is going to be different, all right? So please pay attention. Everybody agrees that that's an angle, right? Cosine inverse should spit out an angle. So what we really want here, we want to try and figure out is what is sine of that angle. So when I write down that theta equals cosine inverse of 1/3, now you run into a problem. What's the problem? What's the issue?
It's not a common angle.
It's not a common angle, right? So this is saying where on the unit circle is your x coordinate 1/3? Now, if it was 1/2, I'd be okay, right? If it was root 3 over 2, I'd be okay. But because it's 1/3, it's not a common angle. Agreed? Okay, but do you agree with this? Cosine of some angle must be 1/3, and we're trying to figure out what that is. So this cosine inverse of 1/3 being theta means that when I take cosine of that angle, I should get the 1/3. Is that okay? Okay, here's the crazy part. Do you remember the definition of cosine when we were talking about right triangles in SOHCAHTOA? What was the definition of cosine of something? It was what over what?
Adjacent over hypotenuse.
It was the adjacent side of a right triangle divided by the hypotenuse. Do y'all remember that? Okay, so what I'm going to do right now is I'm going to draw something. You get to draw, it's going to be fun. We're going to draw what's called a reference triangle. And it's just a triangle that we are going to use as a reference to help us solve the problem, all right? Which is why they call it a reference triangle. So I'm going to draw a right triangle. And I'm going to call this angle theta. And then I'm going to use this right here, that the fact that cosine of theta needs to be 1/3 means my adjacent side needs to be 1 and my hypotenuse needs to be 3. Do you all agree that this triangle is a visual representation of this equation? Right? This equation visually looks like this. Yeah? Now, what is that we're trying to find? That's what we're trying to find, right? Sine of theta? What is sine of theta by definition? SOHCAHTOA.
Opposite over hypotenuse.
Opposite over hypotenuse. So if I knew what this opposite side was, I already have the hypotenuse, don't I? And so all I need to do is figure out what the hypotenuse is. Can we figure out what the hypotenuse is?
By using the Pythagorean theorem.
Yeah, we can. We'll call it, let's say this is like A, right? And this here would be B, and then this would be C. Pythagorean tells us A squared plus B squared is C squared. And so I know that 1 squared plus B squared equals 3 squared, and I can solve for B. This is 1 plus B squared equals 9. That means B squared equals 8, subtracting 1 from both sides. And then B must be plus or minus the square root of 8. And I'm going to throw away the negative. Okay, I'm going to throw away the negative because this b must be positive. And the reason it must be positive, and this is kind of a tricky part, the reason it must be positive is because we have a domain restriction for cosine inverse that we can only be in the top 2 quadrants, which means this triangle we're drawing has to be up here. This b has to be root 8. It couldn't be negative root 8 or else we'd be down here, upside down like that, and that wouldn't work. So now at this point, we can write down what sine of theta is. Sine of theta would be the opposite, root 8, over the hypotenuse, which would be 3. And so that's the answer, root 8 over 3. That problem is very different than the previous two, right? Because it wasn't a common angle, common thing that we could just say, oh yeah, let's just go look on the unit circle. All right. Let's do another one. These are really good problems. How about this? How about secant of tangent inverse of 5? And what I'm going to do, I'm going to take this and copy it. I'm going to go back to this page. I'm going to zoom out a little bit. I'm going to paste that right here. There's a problem I'd like for you to work on right now. I'm going to leave all of that up there so you can kind of see it. And I'm going to give you about 5 minutes to see if you can figure out what this is on your own. You're going to use a similar procedure as we did here, right? See what you can do. 5 minutes. If you finish, I put a problem there for you to mess with. Give you 1 more minute to finish that first one. All right, let's take a look at this. All right, so I'm gonna do this red one first. So I'm gonna work kind of fast, but you let me know if you have a question, all right? So this right here gives us some angle. So at the end of the day, we wanna know what secant of theta is. Now, if theta is equal to tangent inverse of 5, then that means that tangent of that angle theta must be 5. And 5 is the fraction 5/1. And if you think about SOHCAHTOA, tangent is opposite over adjacent. So if I draw a reference triangle and I label this angle here theta, the opposite side must be 5 and the adjacent must be 1. And then if I call the hypotenuse C, we know that 1 squared plus 5 squared must equal C squared. That gives us 26 must equal C squared. So the square root of 26 must be C. Any questions up to that point?
The hypotenuse will still always be positive, right?
Yes, yes. Good question. Yes, the hypotenuse will always be positive. Now, I should also maybe, since you asked that question, I should also point out that because we're talking about the inverse tangent, there is no domain restriction. In other words, we are not restricted as far as what number we can plug in here, because remember, for arctangent, you can plug in anything between -infinity and infinity. So we wouldn't have to worry about, what quadrant anything is in at this point. All right, so now we want to know what secant is, secant of theta. But remember, secant's really just 1 over cosine of theta, right? And cosine of theta, SOHCAHTOA, cosine of theta is the adjacent over the hypotenuse, which for us would be the adjacent side, which is 1 over the hypotenuse root 26. So that's cosine theta. I can put that here. And then I can do 1 over a fraction, just flips the fraction over. So I just get root 26. So if you got that, square root 26, congratulations, good job. Any questions? Let's look at this last one that I asked to do here. So this isn't, when I put the 2 red stars, and I said, this is important. What's important in this is this whole creation of this reference triangle. That is a technique that we use significantly in Cal 2. Well, I don't think significantly is the right word. We use it frequently in Cal 2, all right? But this one right here is a little different because notice I don't give you a number, right? It's just cosecant of cotangent inverse of x. I'm asking you to figure out what that is. So let's try it. Cosecant of cotangent inverse of x. Cosecant of cotangent inverse of x. All right, well, again, this is an angle. Inverse trig functions always spit out angles. So at the end of the day, we want cosecant of theta, right? That's what we want. If theta equals cotangent inverse of x, then would you agree then that cotangent of theta must be x? Just using the same procedure that we've been using. But x can be written as a fraction, x over 1, and I can create a reference triangle. If I call this theta, what is cotangent? If it's the reciprocal of tangent, isn't it? And if tangent is opposite over adjacent, then this should be that flipped over, right? So this should be the adjacent side over the opposite side. Is that clear to everyone? It's the reciprocal of tangent. So the adjacent side should be x here, and the opposite side should be 1, and this side should be c. So let's use Pythagorean. X squared plus 1 squared must equal c squared. So x squared plus 1 must equal c squared. And if I solve that for c, I get c must be the square root of x squared plus 1. So I now have an expression for c that has x in it. Any questions there? So now we have our reference triangle, and let's go up here to cosecant. Cosecant is the reciprocal of sine. And what would sine of theta be off this triangle? Sine of theta would be opposite over
1.
hypotenuse, right?
Yeah.
So 1 over the square root of x squared plus 1. And now we need 1 over that. So we're going to be doing 1 divided by that answer, which flips it over and it becomes square root of x plus 1. There we go. So this is the square root of x plus 1. Sorry, square root of x squared plus 1. All right, so what in the world did we just do? We took an expression that had trig stuff in it, right? This has trigonometric functions in it and inverses, and we rewrote it as an algebraic function. So in your homework, you'll see it says here, these problems here, write each trigonometric expression as an algebraic expression in U. So they use U instead of X. But this exercise right here is basically what we just did. Now, what's cool about this is I can show this to you visually, what we just did. Let me go to Desmos. Okay, so what was it? It was cosecant of arc. What was it? Arc cotangent? Yeah. Of x, right? There's the graph of cosecant of arctangent of x. There it is. Now what I'm going to graph is what we just got as an answer. Didn't we get square root of x squared plus 1? Do you see that they're the same graph? If I take the blue one away, I've got the red one. If I put the blue one, it's right on top. If I take the red one away, right? So they're the same thing. We've converted a trigonometric expression to an algebraic expression, which is kind of interesting. All right, how are we doing on time? We've got 5 minutes. Well, these you're just going to have to get your hands dirty with these. I'm gonna do one last one. This one's gonna be easier than these that we just did. I'm gonna do this one right here. All right, so we want secant of tangent inverse of root 3. All right, so this is an angle. So we want secant of an angle. Theta equals oh man, what's going on here? Theta equals arctangent of root 3. And that means tangent of some angle equals root 3. Okay, is this a common angle? Like if this said sine of theta equals a half, I hope everyone would be like, yeah, that's a common angle. You know, this is where the y coordinate is a half, and that happens at pi over 6, right? Is this a common angle though? That's harder for students to see, but this is a common angle. Let me bring up a unit circle for you. Remember, tangent by definition off the unit circle is the y divided by the x. So where on the unit circle would you have the y divided by x? And by the way, you're only allowed to look in the first and fourth quadrants because this is arctangent. It's between negative pi over 2 and pi over 2. So where would the y coordinate divided by the x coordinate give you that? Does anyone see it?
Pi over 3.
Pi over 3. Do y'all see that? If I take the y coordinate there, what's the y coordinate? Root 3 over 2. And I divide it by the x coordinate, which is 1/2. Then you wind up flipping the 1/2 up as 2 over 1. And then the 2's cancel and you just get root 3. So that means that the angle we're dealing with here is pi over 3. Let me get rid of this. So that means that this angle here is pi over 3. And so what we want up here is secant of pi over 3. Okay, and secant of pi over 3, secant is the reciprocal of cosine. So this is the same as 1 over cosine of pi over 3. And cosine of pi over 3 is the x coordinate here, which is 1/2. And 1 over 1/2 is 2.
You can also use the reference triangle method for this problem too, correct?
Yeah, so what would be different if we did the reference triangle method? Let's see, could we still get the answer? Let's see, if we tried it, if I'll do it in a different color. If we did that and said, okay, this is root 3 over 1, and tangent by definition is opposite over adjacent, then we would have what? We would have opposite side root 3. This would be 1, and then we go solve for c. So 1 squared plus root 3 squared would be c squared. And if we square here, we get 3 plus 1, that's 4, is c squared. So then c would be 2. We'll take the positive case because it's the hypotenuse. So if this is 2 here, and now we just need to know what secant of that angle theta is. And secant by definition would be the hypotenuse over the adjacent, which would be 2 over 1, which would give us 2. Yep, so the answer, Maddie, is yes, you could do this reference triangle. In fact, I like the reference triangle because it just gets you more, gets you ready for Cal 2, but you're just get used to the idea of a reference triangle. Let me see, we're pretty much out of time here. Let me see if I can find something for you here. So your homework for tonight is going to be 8.1 and 8.2. Okay, so 8.1 and 8.2. I'm going to go do those homeworks. And those will be for next time. And then we'll get into 8.3 and 8.4 afterward. Where's my little thing? Where'd it go? I don't see it. Where is it? If you need to go, you can go here in a minute. What I was going to do is I was going to see if I could show you in Cal 2 where this comes in. Let me see here. Does anyone have any questions while I'm doing this?
No, sir.
Trig sub, here we go. So I'm just bringing up some notes that I've done in a Cal 2 class before. There we go. Okay, so in this class, we're trying to solve this problem, and you're going to look at it and not know what the hell it is, okay? But we're doing all this work, and we're using, we do this thing called a trigonometric substitution. So here comes, we bring in a sine function, and we start doing all this stuff, and we start working, blah, 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 blah. Then we get to the next page of work. Here's the next page of work, and we get down to this point, and then we go, okay, we're trying to figure this out. Cosine's in here. And then we say, now we need a reference triangle. And we draw a little reference triangle. And then once we have the reference triangle, then we can finish the problem out. So it's just an intermediate smaller step. Here's the next problem. See, reference triangle right there. Here, different problem. Oh, that's the end of it. I guess I didn't finish that in class, but I can promise you that at the end of this problem, we needed a reference triangle. So they come into play. There's smaller parts of bigger problems later, but if you have no idea of how to do reference triangles, then it becomes an issue. Okay, we good? All right, everyone. Have a good day.
Thank you.
Okay, we'll see you later.
Thank you.